All right, so for Chapter 8 worksheet problem number 2, we have this rectangular prism here, and there's a force of 150 pounds applied to the edge of the member as shown, and we're told to neglect the weight of the member and to determine the state of stress at points B and C. B is over here on this corner, C is over here, and since it's fixed at one end and free at the other, what we're going to do is analyze this in a more simple way. So we're basically given a 3D rigid body, again, fixed at one end, free at the other, and we have an applied force that's off of the centroid of this rectangular cross-section. So it's not acting right in the middle. We're not only going to have an axial stress. What we'll see is we're going to have a bending moment. In this case, if we draw our free body diagram of this top section, just cut through this cross section where B and C are located, we're going to find that if we sum our forces in the Z direction, we get this normal force here. Our internal normal resultant is going to be a compressive 150 pounds. So the direction I drew it here was incorrect. We got a negative. That's telling me that it's not tensile as I drew it. It's compressive. Sum our moments about the X direction. We get that a moment where your thumb is pointing in the positive X direction is going to be 150 times this moment arm away from the X axis. So this is a Z force times a Y distance, the way I drew the axes. So your moment is 750 pound-inches. Okay, so in our other two directions, X and Y, we don't have any forces, so those would have been shear forces, but they don't exist. We don't have any bending about the Y-axis because the 150 is on the Y-axis. That's the axis going through the centroid. And then we don't have a bending moment about the Y-axis or the Z-axis. The Z-axis would be a torque, technically, but we also don't ever talk about torques in this class on anything other than circular cross-sections. All right, so what happens if we have a normal force and a moment? Well, we're going to have normal stress due to that axial normal force and normal stress due to that bending moment. And we'll have to look at both B and C to see what happens. So we'll look at the cross-section. This is drawing it from the same way we had, but just getting rid of all this extra volume that we don't really have to look at. So B is still down here, C is up here. Right? We find that our axial stress is N over A, that's our equation. Plug in our normal force, it's compressive, so we have a negative 150, and then the area is just 10 inches times 4 inches, it's a rectangle. And you get an axial stress of negative 3.75 psi. The negative there is just indicating, again, compressive. We have a compressive normal force, we have a compressive normal stress. Now, at point C, the bending to this moment about the x-axis is going to be our flexure formula, negative my over I. And here we need to consider in what way are we getting rotation about that x-axis. Basically, we found that the moment where your thumb is pointing in the positive x direction is one that's going to cause compression over on this side of our cross-section. So our centroid here, neutral axis here, means we're going to be in compression at C and tension at B. So this arrow for our moment is showing that it's bending it toward C, so that part's going to be in compression, and B is going to be in tension. We have the same Y value for both C and B, but if we're following our typical flexure formula sign convention, Y for C is a positive 5, Y for B is a negative 5. So the negatives cancel here. We get a tensile stress for B, but a compressive stress, once again, for C. Now all we have to do for the combined stress is add them up. So at B, we have the same axial stress. No matter where you're at on your cross-section, your axial stress is going to be the same, so negative 3.75. And for C, same thing, negative 3.75. But at B, we're going to add with 11.25 because it's tensile. And at C, we're going to subtract it. So you just add those up, and you get a positive 7.5 psi at B. So that's going to be tensile. But you get a negative 15 at C. So that's going to be compressive. And that's really all there is to it. So again, combined loading problems, we're going to do our statics to find our internal resultants. And then we're going to look at our cross sections to see how those internal resultants affect the stress on the actual cross section at certain points. Right? And later problems will draw elements of the material at those points and draw our stresses on those. All right, that's it. I'll see you on number 3.